Hi, I am Sriram Vignesh Mani, and today I'm going to talk about ant colony optimization and its methodologies. The picture here clearly shows the technique based on which the ant colony optimization method has been developed. This picture represents the group behavior of ant colonies. It is clearly visible that ant colonies take the shortest path between their home and the food source and back to home from their food source. The ant colonies behave based on optimization technique. Based on the technique, all the ants communicate among themselves about the quality of the path they travel. Based on the quality of the path they travel, the ant colonies decide on an optimal path connecting their home and the food source. This video also includes the methodology required to employ ant colony optimization method and also an example problem in which the technique has been applied. The contents of the video are organized in the following manner: introduction, biological inspiration, methodology, problems solved, and applications. Ant colony optimization is a member of the swarm optimization methods. Swarm optimization methods are methods that are developed based on observing the group dynamics of natural systems like ants, bats, and bees. The general methodology of a swarm optimization methods are described here. Each of the swarm optimization methods consists of a number of candidates or searching agents, and each candidate or the searching agent walk randomly through the given search space, generating their own set of solutions. Each candidate solution is then optimized based on the current value to arrive at the best solution. This slide briefly describes the biological inspiration based on which the ant colony optimization technique has been developed. For simplicity, let us consider this picture. Let the blue hill represents the ant hill and these three drops represents the food source. As can be seen, initially all the ants move in a random manner, depositing pheromones along their travel path. Each move of the ants can be considered as a part of Markov chain, because the probability of the move depends only on the current value and not on the previous values. An important property of the pheromones is their ability to get evaporated in the course of time. The concentration of pheromones is highest in the shortest path, as the ants traveling in the shortest path can travel more number of times between the food source and the ant hill and depositing more number of pheromones on each of their travel. The high concentration of pheromones gradually attracts all the ants towards this path and thus makes this path as the optimal solution connecting the ant hill and the food source. The longest path with the least amount of pheromones gets deleted from the ant memory in the course of time. Ants thus forgets these paths and starts exploring the search space for other directions. This is an important property of the ant colony optimization and advantage over other optimization techniques. This helps the ant colony algorithm to come out of the local minimum and search for the global minimum. This slide briefly describes the type of problems that can be solved using the ant colony optimization algorithm. Initially, this method was developed to solve NP-hard combinatorial optimization problems. Combinatorial optimization problems are those problems in which the independent variable governing the objective functions can take only discrete values. Examples of such problems are traveling salesman problem, vehicle routing, and scheduling. Later, these methods were extended to take continuous domains. That is, the independent variable can take continuous values. Now let us see the methodology of implementing the ant colony optimization technique. As described, there are different variants of ant colony optimization technique. Some of them are ant system, ant colony system, or max-min ant system. The variant that has been discussed here is ant system. For the convenience of understanding, let us consider the example of traveling salesman problem, in which the salesman has to travel through a number of cities in the shortest path possible, and he has to travel through all the cities exactly once. Hence, in this problem, the objective function can be considered to be the total distance traveled by the salesman, and it has to be minimized. This is an example of NP-hard combinatorial optimization problem. In order to represent this NP-hard combinatorial optimization problems in a graphical form, each city the salesman visits can be considered as a point or vertex in the graphical problem. and the path connecting the two different cities can be represented as edges in the graphical problem. As already mentioned, each of the path is randomly distributed with the pheromone concentration initially. As discussed earlier, a large number of ants starts randomly from random cities and they walk through random path, thus generating each of their own set of solutions. Each of their own set of solutions are generated based on the constraints given. The constraint given here is that each ant has to travel through the city exactly only once. The probability of selecting another city from the current city is based on a given probability function. The probability function for choosing city j from current city I is given by the following expression. Pij represents the probability of going from city I to city j by the ant k. Tau ij represents the pheromone concentration associated with the path connecting the city I and j. Eta ij represents the heuristic information available about the path connecting the city I and j. The heuristic information can be calculated using the following relation. Here dij represents the distance between the two cities I and j. If the distance between the two cities are very less, then the heuristic information for the corresponding path is very much higher and vice versa. Based on the values of the parameters, the probability function can be analyzed in the following two ways. If the value of parameter alpha is 0, then the probability function is purely dependent on the heuristic information available about the path connecting the cities I and j. If the heuristic information for the path between I and j is very much higher, it means that the cities I and j are very close to each other. This type of probability function results in choosing only those cities that are nearer to the current city. Thus, ant colony optimization starts behaving like a greedy algorithm. If the value of parameter beta is 0, then the probability of going from I to j is purely dependent on the pheromone concentration associated with the path connecting the cities I and j. Such type of probability functions can generate localized path and limits the search space. Once all ants travel through each of the cities, the next logical step is the pheromone update. Pheromones associated with each vertex is updated using the following relation. Here, rho represents the evaporation rate and it prevents in accumulation of pheromones along a particular path. Delta tau ijk represents the amount of pheromones that need to be added or subtracted to the path traveled by the ant k. It is calculated based on the following expression. Here, Lk represents the total length of the path traveled by the ant k. If the total length of the path traveled by ant k is very much less compared to the path traveled by all other ants, then delta tau ijk for the ant k is going to be very much higher compared to all other ants. This high value of delta tau ijk is added with the path traveled by the ant k. This results a high amount of pheromones in the path traveled by ant k compared to all other ants. In this manner, the algorithm proceeds. With each iteration, a suitable value of delta tau ijk is added to the paths traveled by each of the ants. In the due course of time, a path with high concentration of pheromones is considered to be the optimal path for the given problem. This slide briefly tells about the application of the problem to which the ant colony optimization technique has been employed. The problem at hand is air traffic conflict resolution. According to this problem, n aircrafts located along the circumference of the circle are traveling towards the center with the same velocity or speed, and each aircraft has its destination along the same diameter represented in the circle. This is an NP-hard combinatorial optimization problem. The objective of this problem is to minimize the path traveled by all the aircrafts in such a way that none of the aircrafts meet each other in the conflict zone at the same time. Ant colony optimization technique has been employed by the authors to solve these problems. The solution proposed by the ant colony optimization algorithm is pictorially represented here. The algorithm proposes a horizontal deviation along the flight path for each of these flights, satisfying all the constraints. That is, each flight has to travel through the minimum path possible, and none of the flights meet each other in the conflict zone at the same time. Thus, to conclude, in this video, the basic methodology and the applications of ant colony optimization technique has been discussed. A practical problem to which the ant colony optimization algorithm is employed is also discussed in this video. Thanking you.